Okay. Good afternoon, all course participants of this workshop. Good afternoon to all of you. In the second half afternoon, the first session, which I am delivering on digital soil health for smart agriculture. As we know that today entire world is talking about the precision agriculture, smart agriculture, or digital agriculture. Means where in the agricultures we employ the technology, information technology, then and more informations using geospatial information, then it is known as a smart agriculture. And as in forenoon session we told that soil health is a important to know for its sustainable use. If health is declining, then something is wrong in our agriculture land use plan, or because soil to sustain the life for the coming generations as well. So it is our prime responsibility to keep the health of the soil intact, or we should work for the improving the health, but if not improving, at least maintaining the soil health is our foremost responsibility. So with this note, I just start my lecture. Smart agriculture, if we see that one, 10,000 BC, we were calling that was a agriculture 1.0, where we were using simple tools, manpower, and animal power for our agricultural activities. Then comes 19th century, we term it is agriculture 2.0, when we have started use of chemicals, fertilizers, machineries in our improving the nutrient content in the soils and improving the fastness or easiness in agriculture activities, operational activities. Then lot of machines came, tractor came, and that is your animal power is reduced somewhat, and we are witness of that one. Once upon time, in earlier time, we see that is the mainly the animal power was the prominent in agriculture, but in 19th century we see in the last 20 years back, uh, this has been replaced with the machines. Then comes agriculture 3.0, that is the 20th century, and you see here we started because in 20th century there is an invention of computer, electronics. So these were enabled to use in agriculture, and you can say the remote sensing, GIS or geospatial technology comes under agriculture 3.0 in 10th century. And we use geospatial data, computer applications for many of the operations of agriculture, productivity, functions, and other things. Then now we are moves towards 21st century, and I term it is agriculture 4.0. Here we are using advances of information technology. We are calling it is Internet of Things, big data analytics, cloud computing, artificial intelligence. Now this has been taken the are being used immensely in the very not only the agriculture sector, but various industry sectors and other things. And agriculture cannot be untouched, and all this technology is being used to agriculture and realizing the new generation agriculture using smart devices and smart system, and we call it is digital agriculture, smart agriculture. If we see that in the agriculture, one thing is that we should aware that 18% of gross domestic product of the country, GDP, is come from the agriculture, and it involves around 57% of the population. People depends on the agriculture, and you can see the GDP's contribution is very less, and people's dependency is very high, around 60%. So, and over the period of time, now we see the grower or farmers has declined from 71.9% in 1951. 79.9% were the farmers, and in 2011 statistics show only 45% are the farmer. And we have in economic survey 2018 revealed that the number of agriculture workers of the total force will be dropped 25% by 2050. So 45 becomes 25%. So why it is happening in rural areas? We can see the farming family gradually losing the interest. So next generations farmers will because are not will be there, or they are losing their interest in the agriculture because the agriculture is not profitable, higher cost of cultivation, per capita productivity is low, inadequate soil maintenance, because we are harvesting from the soil, we are not putting enormous effort to the soil productivity. So how long it can sustain? And migration of non-farming or higher, people are migrating to the other activities where they can get more income. So presently the world is on the verge of digital revolution. We are getting various technology, and in appropriate time to connect the farmers. Unless farmers are not given these smart technologies, they were not enabled, then they will not do the farming, and we cannot improve our crop productivity as well. So the wireless technology is making connecting the farmers as a digital connectivity. So you can see here, for sustainable agriculture, three components are there: society, environment, energy. Society needs energy, and for energy, when you are needing, then it is affecting your environment. And this triangle, if we if we make the balance, then it will be your lead to the sustainable agriculture. So agriculture 4.0 era, the adoption of new technology, which has significantly improved the agriculture activities, because now we are developing low cost sensor network platforms. And how, why what the what how they are helping low cost sensor? They are helping in the optimization of production efficiency, reducing the reducing the water resource wastage, energy, and minimal environmental effects. So if we, every resource we will use in optimization, means right amount of fertilizer, right amount of pesticides, and efficient use of water. Unless we are not bringing into the production system, then our agriculture will not be sustainable, or agriculture will be not environmental friendly, and it will be not energy efficient. So therefore we need to adopt this new technology, and is a digital agriculture. The smart agriculture, it requires real time data of the crop, means you need 5 month 4 month crops is there, from starting from sowing to the harvesting, different crop growth stages. I want to know the condition of the crop, so that I can make the assessment of the water requirement, assessment of nutrient requirement. And for that one, you need monitoring of the our crops, our resources. That's why I told you in the morning that GI set, government of India, ISRO is planning to launch GI set, the new satellite, where you will get everyday remote sensing data, so that you can monitor your crop growth daily basis, so that any disease, any stress, either it is nutrient or pest disease stress, that you can monitor, and you can make a contingent measure at the right time. So the smart agriculture is considered as a progression of precision agriculture. Sometimes people are calling it as precision agriculture, because we are precisely inputting the inputting the uh, fertilizers, pesticides, and other water in the at per their requirement. So real time farm maintenance solutions is the clue for sustainable management of agriculture. So means precision, precisely what the crop required, that amount of the input should be put into that one. It will improve our efficiency, economic efficiency, and it will reduce the wastage. So if reducing the wastage, it means you are helping to the environment. So all these things are linked together. So you can see that the smart farming wheel, that is the sensing there is a six components are there: sensing technologies, software application, communication system, means your mobile or other, telematics positioning technology, means GPS systems. So precise geographic information is important part for application, because tomorrow we are talking about the drone application. So drone will 40 we are aware that 40 drone or fertilizer applications are being done by drone. Even seed applications are doing by drone. So how it is possible? Because unless you not have the geographic proper georeference thematic data, then on the basis of that one, it will position the spray or application of the pesticides or fertilizers or anything. And for these all these things, you need a hardware and software system. So you can say the computer science has actively involved in the smart farming or smart agriculture, because as with the development of computer technology, all these things are being possible. And now the software technology means data analytics solutions, because AI, machine learning, artificial intelligence, and various techniques which are coming today, they are making the solutions. They are analyzing the huge data set, because you are every day you are collecting the data, environmental data, climate data, soil data, crop condition data. So data becomes very voluminous, and to analyze those voluminous data, human mechanically it is not possible. So that's why software are required. So these are the component of the smart agriculture. So so we see in the case of geospatial technology, we need to have the soil information improved soil information, because soils having the what kind of soil is, what texture is there, what is the pH of the soils, what is the depth of the soils are there, what is the soil nutrients, means major nutrients, micronutrients are there, how much soil carbon is present into the soils, electrical conductivity of the soil. So morning what you I told you, physical, chemical, and hydrological property as well as biological property also, we need to know about the soils, so that those informations we can utilize to assessing the soil health or soil potential, and so that we can infer a proper knowledge, proper informations for making a plan. So for that one, remote sensing, I told that multispectral remote sensing data, hyperspectral remote sensing data, proximal sensors. Today, many of the proximal sensors means direct in situ measurement of the nutrients. Various proximal sensors has come. For example, that is the X-ray fluorescent meters, that is you put onto the ground, and it can tell you the micronutrient status of the soil. So proximal sensors are now becoming more and more used. You have the old data, legacy data, you have the ancillary data, and these data you are getting from various sources. And these data, then you are using data analytics techniques, data fusion, web services, Google Earth Engine, data analytics, and all these you are putting into the geospatial models or statistical analysis. And then you know these parameters, Some parameters are linearly related to the information, some parameters are non-linear. How it is linear, non-linear, then you need a data analytics or machine learning techniques, and they simulate and they provide you the improved information about the soil, physicochemical characteristics or physicochemical conditions of the soil, temporal variation. Suppose there is a salt affected soils are there, and you know salt affected soils, in every month the salt content in the soils are changing. So how they are changing, where which time they becomes the highest salt concentration, so that informations we want to know for its better management. So temporal characteristics of the soil, dynamic properties, those properties which change with the management system. You are changing the land use, you are changing the crop type, you are changing the irrigation method, you are changing any operational activity, then how they will affect your soil properties. So that you can get from the remote sensing sensors, dynamic properties, and then you can also integrate it together. You can analyze for the ecosystem analysis, and ecosystem is agriculture ecosystem. So today we are not seeing only soil system, we see crop system, and all together climate system, and climate, soil and crop, all together three systems together we make agriculture ecosystem. Because we have to think as a whole, because soil is not providing you the only the agriculture production, but they are giving you the environmental security as well, they are giving the climatic security as well against the climate change, it is giving water security also. So it is total ecosystem is getting affected by the soil, and that's why the soil, we are so much of concern about the getting the information, improved information about the soils, so that we can efficiently manage the soils for sustainable agriculture. I just saw some of the proximal sensors which are coming to the market. Here it is showing the NDVI meter. Direct spectroradiometer reflectance is converted into NDVI, or from NDVI you can get from the value of the NDVI that can help you to get the crop condition. Means where NDVI value range from 0 to 1, and if you are getting more than zero point 0.7, then you can say the crop condition is very good. And if you are getting less than 0.2 or 0.3, then we can say it is a very poor crop condition, and in between that is you can say the moderate. So with the NDVI value, your if you are getting local also you can measure, spectro satellite images you can measure, you can use the UAV also for preparing the map, and you will get the NDVI image map, and you can classify it into the different crop condition crop condition classes. This is LAI meter, leaf area index meter. This instrument is used based on the reflectance model only, and we put on the top of the crop and put under the crop, and we get the how much radiation is on the surface and reaching to the downward. So that helps us to find out the leaf area intensity or leaf area index we can use. Here once given that is the wet sensor, this wet sensor theta probe, we call it is theta probe, and you can find out the soil moisture content, wetness. E means electrical conductivity, salt concentration. T means temperature. So you can measure with this temperature, electrical conductivity of the soils, and soil moisture instant. So need not to bring the soils at your laboratory. Their field itself you can find out those informations. So you can actually this sensor helping you to get number of points, large number of points data sets, you can collect the information, and then you can generate the thematic map by various methods of machine learning or geostatistic or any other methods. Here it is shown you the portable visible near infrared spectroradiometer that can be used, and you can get the spectra directly and you can utilize. And here it is shown the UAV. You can in UAV also your multispectral sensor or hyperspectral sensors are mounted, and you are getting the reflectance in those spectral wavelength region. So it is is imaging type spectroradiometer. Another that you are saying that is the we are using the electromagnetic sensors as well, where to get the soil properties. For example, soils, you are having the non-contact electromagnetic sensors for soil mapping. So it is a it provides you the salt concentration into the soils, electrical conductivity, or the, yeah, sometimes it provides the subsurface informations in that. So it can be mounted on the tractor itself. And also we know that is the ground penetrating radar, GPR. GPR, if you take the GPR survey, then it tells about the soil subsurface moisture, and any concretion depth is there or impermeable layer within the soil is there, which from the surface we are not able to see. That can also be you can get from the GPR or ground penetrating radar. Here the instrumentation is there for soil pH mapping, electrochemical sensors are there. So there are various sensors are in the development, and the companies are preparing and testing in the laboratory. Although these sensors gives a quite reasonable results, but still the technology is not very handy. It is not cheaply available, or it is not easily available to the users. You can say the more in experimental stage, and and in very soon this technology will be becomes in the hand of the farmers, so that he can get more and more information. uh, we can get the soil test also with the strip, and someone has developed this soil test kit also, with a reasonable accuracy. You cannot compare this accuracy with the laboratory data. Here you can get only the qualitative means you can categorize into slight, moderate, severe, and very severe conditions, means classes you can find out. But for the management point of view, this information is quite is useful pretty well. So smart agriculture, that having the components of three, I have divided into three part. One is the application. One, you want to monitor the soil monitoring, nutrients monitoring, water content monitoring, pest monitoring, environmental monitoring, and farm operation monitoring. These are the applications in the smart agriculture. Facilities, you can say soil evaluation, means fertilization, when to do fertilization, irrigation, insecticides, weedicides, yield monitoring we want to do, storage and marketing, because this is the you need to develop the facilities for storage, marketing, all those things for smart agriculture. Smart means not only that is that we have grown the crop, and after that production is taken place, and you have not properly stored it, then it will get wastage. If you have not marketed well in the market, then you will not get a good price. So these facilities also need to be provided, and that's why this is also a part of smart agriculture. Means pre harvest management for improving the yield and getting the maximum yield is one part. And when you get the yield, then for its further facilities also required to get the maximum price to storage. And this you also need to have the storage of fertilizer, irrigation, supply water, and other things, that if you are developing these facilities will help to you getting smart agriculture. What are the devices are today available? Today soil sensors are available, nutrient sensors, moisture sensor, chlorophyll sensor, temperature sensor, and remote sensors, means NDVI meter, for example, LAI. Robots are also being tested in the developed countries. They are using lot of robots in agriculture, robotics for the pesticide applications, or precise nutrient management they are using. And communication, because once you analyze those information, then it has to be reached to the farmers, so that you can do the communication media, that is also part of the smart agriculture. So AI technology are emerging to help in improving the efficiency with respect to crop and soil monitoring. Weather forecasting is also a part of smart agriculture, because what will be the weather conditions tomorrow, after 1 week, after 15 days. So that weather conditions will help us to for taking the action for irrigation, or storing the harvested product, or agriculture management practice, management operations. For that one you need a weather information. So weather forecasting is also a part of smart agriculture. Predictive agriculture analytics means uh, various analysis, whatever the agriculture informations you have to make the predictions over that one. And market and supply chain efficiency, that is also part of the smart agriculture. And how this can be get, that is the cloud computing infrastructures with the use of data ecosystem, internet of things. All these things are helping us to bring the agriculture as a digital agriculture. So you can see here, that is how a farm is there. You have the UAV, you have the digital camera, thermal infrared, hyperspectral camera, multispectral camera, proximal sensors, all these things. You are getting the enormous information of the crop, of the agriculture field, and these data should go to the mobile node. eh? So here also on the ground you have ground wireless sensor nodes also, means soil moisture sensor, nutrient sensors, and soil moisture sensors you are installed in the field also. And you have the AWS information, automatic weather station, and those data is going directly to the going to the cloud, and it is going to you are doing their data analysis, data processing, data storage, and distributing this information through communication for various applications to the farmers. Pest control time, pest management, yield prediction, precision irrigations, precision fertilization, or agriculture management. So all these things we can do, and the technology have been demonstrated very well. But this technology requires large farmers field, and there is some constant why we are not able to use in our Indian conditions. But in India also, smart agriculture is being used. If you go to the Odisha, Bangalore, Karnataka, you go to the Maharashtra, for particular crops, in few crops, the farmers are dedicatedly using this technology for improving the production and crop production, and improving the efficiency of that one, and they are getting benefited over that one. So it is not that only the, I can say, that is in the papers it is available, but it is has been realized on the ground itself in India also. So here I will say that according to the report published by the National Association of Software and Services Companies, we call it as NASSCOM, in 2019, there were more than 450 agriculture based tech driven startups were present. By 2019 it was there 450, and now it may be nearly to the 700, or maybe reaching to 1000 agriculture based startup who are dedicated to the smart agriculture. Agri based technology driven startups are making revolution in our farming technique, and I will come that which are the companies are there, I will just tell you. So you can see here that according to the Ministry of Agriculture, the government is taking various smart agriculture initiatives, such as one initiative, Niti Aayog, in 2018. They partnered with the IBM for developing crop yield prediction model using AI. So they make the collaboration with IBM, and pilot studies were carried out to predict the crop yield, and the crop yield prediction models with AI they generated, and this helps to providing the real time advisory to the farmer. So because crop condition assessment at various crop growth stages, they have they simulated, and they find that is the what will be the crop yield will be there. So because if crop yield is going to be better, then only farmers will invest. So you have to tell crop condition every crop growth stages, that is the how crop is performing, so that you can get the best management. This is one project is gone. AI sensor for smart farming. Indian government partnered with Microsoft for empowering farmers, small holder farmers in India. This partnership would help to boost the production of AI in farming. So this experiment pilot studies are going on, and they are trying to know that is what is problem in the field and how we can utilize this one. Another program is going on, drone for monitoring soil and crop health. The government launched a program that is known as a sensor based smart agriculture, sensor based, involving 6 institutes. In this project, drone will be used for smooth scouting over the landfills, for collecting the precise information and transferring data to the farmers on real time basis. So you can say the drone based multispectral sensors were used to assess the crop condition of each and every field, and those informations was analyzed, and the crop condition means the crop is getting diseased, or insect infestations, or deficiency of the nutrients, or weed infestation, whatever the problem is getting. So they try to find out with that one, and they given the informations to the farmers to take the appropriate management operation. So yeah, in this one, the 6 institutions involved were Ministry of Communication and Information Technology, Department of Electronics and Information Technology, Information Technology Research Academy, and Indian Council of Agriculture Research. And thus the and government is today also providing the financial support to agri-tech startup and aim is to adopt this AI to revolutionize the agriculture and farming trends. Some companies has also made some you can say the solutions. Agropad, it is artificial intelligence powered technology helping farmers check soil and water health. Agropad 10 developed by IBM, and here they have developed one microfluids chip inside the card, perform on the basic and on the spot you can do the chemical analysis of soil, and it provides the nutrient status, some nutrient status. Another you may be aware that is Plantix is being used by to crop disease identification. So many times which disease is there we don't know, and those expertise is not there, but they have the library of plant diseases, and you just take the pictures and you can analyze and find out the diseases. Pay for per use based farm technique and mechanization. So there is a Tringo company is there, or EM3 Agri Services. These there are two pioneer farm equipments, and they are providing the farm equipment on rental basis. So no need to purchase the heavy instruments because we cannot bear the cost. So one instrument can be used many places. So on rental basis, this company has started renting farm machinery and tractor in India. Use of drone to fight locust in India. So locust control, we know that is from the Afghanistan and in the Rajasthan area, locusts are infested our countries this part. So ministries are using the drone for identifying their movement and their conditions, so that they can monitor their movement, so for taking the appropriate actions for the management control of the locust. So this is the I told you the IBM developed the AgroPad prototypes, This is currently they are using to measure the pH, nitrogen oxide, aluminum, magnesium, in some nutrients, but not those nutrients which we are interested. For example, soil carbon, nitrogen, phosphorus, potassium, those are not available. They are trying, but it is there. One important development done by ICR with the collaboration with the IRI, and one instrument is available, PUSA STFR meter kit. This is the complete solution for the analyzing the soil sample for the major nutrients, organic carbon, and all micronutrients. So for the soil health, whatever the properties you want to know or you want to analyze, all the properties can be analyzed using this instrument, this kit, PUSA STFR meter kit, and it's cost around 2 lakhs rupees, and you can analyze many number of samples here. You can get the print of the results also, so everything is there. And we call it is a soil testing kit, is a soil doctor, which provides the 14 parameters of the soils and recommends fertilizer dose also for over 100 crops. So your soils is deficient, then which is nutrient deficient, and for if you want to take X crop, then which how much fertilizer is required, that recommendation is also feeded into that one. So it is helping to the farmers to get the recommendation also. So that's why it is soil doctor, and that has been used in the soil health card program also by the government of India. Now I will go towards showing some case studies related to soil quality and health assessment, how we can use geospatial data in soil health assessment. So few case study I will show you. One case study is from the hilly area. You know, this is the digital elevation model, DM, and from DM you can get the elevation information, slope, aspect, terrain wetness condition, terrain wetness index, stream power index, sediment transport index, specific catchment area. So those are very easily you can prepare the slope map, and you can generate the TWI, or also we call it is topographic wetness index. So means where water getting accumulated, and these information or these maps we can use to know the to in distribution of nutrients. So here you see what has been done there, the soil sampling. We have done the soil sampling, grid soil sampling, taken the samples here around hundreds, more than 100 samples, and then by kriging methods we can find out the total carbon distribution, phosphorus, available phosphorus map, nitrogen map. So you can see where is the distribution of carbon, nitrogen, phosphorus. So suppose here it is showing that is yellow color, low carbon and low phosphorus, and here it is showing the high phosphorus content. So where if agricultural land is here and then it is a low phosphorus, then the fertilizer applications, this map can be utilized. So now application of fertilizer management, and for details if you want, then you can refer this paper which we published in environmental earth science, that is how distribution of soil nutrients can be mapped using digital elevation model. We use the geostatistics. Here we use the NDVI map and terrain wetness index map as a ancillary data. So we call it is when we use other map for kriging, then we call it is co-kriging. So it is co-kriging map, and it gives a good accuracy in the hilly and mountainous landscape or hilly landscape. How we do that one? So I told you that is the digital, the one of the technique, that is digital soil mapping being more prominent, that one today. So suppose you have the grid, and this grid you have the suppose these are the grid, and some points you have collected the soil samples and analyzed the physical chemical properties of the soils, pH, EC, or any properties, and you have the remote sensing data, and from remote sensing data you can generate the environmental covariates, Environmental covariates, you can say from remote sensing data, you can generate the spectral indices related to vegetation, spectral indices related to the soil, and terrain wetness index or terrain indices you can derive from the digital elevation model for the same area. So you can generate the environmental covariates. You can generate the you take the sampling and you can generate the soil information. From soil informations you can calculate for I have shown here so many of points, but suppose you take it 50% 50% points, you can take the samples, and for the 50 that point you calculate the soil quality index. How to calculate the soil quality index I will tell you in next slide. So soil quality index you can calculate and you can get this one, and want to prepare the map using that one, then we soil quality map and environmental covariates, both maps are taken, and then you do the machine learning techniques, or you do the linear regression, random forest model, artificial neural network, expert system, geostatistical methods, kriging or co-kriging, and you can prepare the soil quality map. I will show you how you can prepare. Suppose this is the one area. This is shown the it is the of Mandi district of Himachal Pradesh, and this is a false color composite, and this is the mainly the dominant agriculture area. So in the agriculture area, we have taken the some points. We have taken the soil samples where the you are saying we plan the grid, and some of the grids where we can reach, where we can we have taken the soil samples, so it is shown that is the soil sampling points. So surface and subsurface soil samples were taken. Then you go to the laboratory analysis for nitrogen, phosphorus, potassium, soil organic carbon, electrical conductivity, and pH of the soil. And then you give the rating to each properties. Rating, how we will give the rating based on its value. Suppose soil organic carbon is the what is the highest amount of soil organic carbon present in those into the entire area, that highest amount will be used to divide the other organic carbon content in the soils. So we get the ratings of that one, and then we give the weightage. Some all properties cannot be give equal weightage, but some properties for the soil health or soil quality requires high weightage. So here in the hilly area, electrical conductivity and pH was not having much weight. Here the soil organic carbon and nitrogen, phosphorus, potassium having the high weight. So we given the weight, and we for that one we use the one technique, that is analytical hierarchy process, AHP. So you see that we have given the weight based on the highest weight to soil organic carbon, then nitrogen 23% weight, phosphorus, potassium, clay, and pH content. And once you have weight and ratings, then you can calculate the soil quality index using this formula, that is the summation of is S is means the score, or you can say the rating, and W is the weightage, and you can make a summation of that one of n parameters, how many parameters you have decided through AHP. So those parameters you can take 5, 10, or whatever the relevant parameters you have decided. Then you can calculate the soil quality, and then first you prepare the geostatistical by kriging methods. Here it is prepared, that is the soil organic carbon map, total nitrogen map, it is the soil phosphorus map, and here soil potassium map. So we have taken only 4 parameters here, because these 4 parameters are important for soil health when you are assessing the soil health, because for the current management point of view. And then we given the scoring and the weightage, and then integrated to calculate the soil quality index, and then we generate this map by integrated map. You can see where more than 75, red color is showing more than 75 soil quality index, it is coming from 0 to 100. So more than 75, this you can say this is the high soil quality, and here this dark color, it is showing the lowest soil quality. So it having the lowest soil quality, it is having the highest. So this preparing the soil quality index map or soil health map In that way, you can find out that is the fertilizer recommendations of crop management, agriculture management. So this is the soil quality. You can find out in your area how much area under high quality area is only more than 75%, only 5.46% area is under high soil quality. So this generating this information, this map can help you for your fertilizer management or providing the fertilizer to the soil. So you can use once you have georeferenced map, this soil quality or soil health map, then you can use the drone and fertilizer. This map can be fed into that one, and then fertilizers can be applied appropriately. So for drone will apply where low quality is there, it will apply more, and where the quality is high, there it will apply low. So you can make a fertilizer efficiency, you can improve the fertilizer efficiency, otherwise your fertilizers may go waste. So you can reduce the cost of the fertilizer or fertilizer application, so you can improve your economic efficiency. Another case study I will show you, that is here we use that is for geospatial technology for site specific management zone. And in Uttarakhand we did, this is the digital elevation model, and where we can reach, we have taken the random soil samples, where we can reach the randomly distributed soil samples in the entire area we have taken, and then we have used a fuzzy C mean clustering algorithm to find out the management zone. So here you can say using fuzzy C clustering methods we generated the soil pH map, soil electrical conductivity map, soil clay map, soil potassium, phosphorus, nitrogen, total carbon, slope. These are the slope and NDVI map, but these are by the interpolation of that one. So not interpolation, we use the slope, NDVI, elevation for the fuzzy set clustering techniques, or you can say the fuzzy C mean clustering algorithm was used to group those points, and we generated this map. So you have generated so many of maps, and then these maps was integrated together. First individually it was generated by kriging, and then it was collectively integrated using fuzzy C mean square, and then you generated the groups and you find out the management zone. It is showing that is that this area is one management zone, this area is another management zone, MJ4. So we deleted the area into 5 management zone, and it says that is the you do the these soils are similar in their soil health or soil quality, and here the management is different, here the management will be different. So what kind of management is there, then based on these characteristics you can define the management practices. So you can say the geostatistical methods you can utilize for generating the individual map, and fuzzy C mean clustering you can utilize for grouping those informations into converting into the management zone, and this management zone can be utilized for efficient agriculture or minimizing the cost of cultivation. Here another one study I show you, the we can estimate soil quality parameters using proximal sensor. Here you see this is the small instrument is there. We know the mobile based color sensor. Name is Nexpro. This instrument is simply measure the color of the soil. So color of the soils, or with the color of soils we can measure color into the quantitative term, not qualitative. So we measure the color into the in the RGB values were first converted into the CIE XYZ with locations, and this color. So with color I want to predict the carbon content into the soil. So what we have done, we have measured the 2000 number of soil samples, and we of same samples we were having the data of carbon, nitrogen, phosphorus, potassium and clay, and then we try to find out, can with the color, soil color, can we find out the nitrogen, phosphorus, potassium or carbon content into the soils? Yes, these instruments we can use for without analysis of the soil in the laboratory chemical analysis, just with the measurement of the color you can get the information about the nutrient content present into the soils. So we find that in the organic carbon we are able to predict with accuracy of 0.7 r square, and nitrogen we are able to predict 0.67. So we found that the organic carbon total nitrogen can be predicted very well with this instrument, just measuring the color of the soils, and color of the soils with this instrument is measured with the you can say the quantitative term, and these are the relationships has been established. So we can see that there are various benefits for the digital soil health monitoring, and that you can say the real time you can get the information. You can use this information for precision agriculture, sustainable land management. But there is a barrier, there is a problem in implementing smart farming technology, because the major barrier is their cost of technology. This technology is still, with this time, it is costly. It requires a lot of money, huge money investment, and our farmers are not cannot afford those costs. That's why even we need informations, but we are not using. Literacy status is also one of the problem, because these are the instrumentation, and it's you need to understand those instrumentation. So literacy status is one problem. Lack of integration between the system, because there is a complete gap. You can say that there is huge gap between the companies developing the technologies and academics and the user. All three are not in a coherent way. That is, the academics sometimes using with the industries and using for the research purpose, but it is not implementing to the farmers community. So this integration has to be looked after. Telecommunication infrastructure, although in India all the villages we are getting the 4G 5G link is there. So because using the your telecommunication media, but for transferring the data fastly to the to those, so in a real time basis is still it is time to work on that one. So internet enables, you have to make. Data management is one of the serious problem, because data from the farmers, data from the companies generating the informations, they have to be clubbed and to generate with the process informations, and it reach to the farmers, and farmers can in the farmers language, so that he can use those informations. So in the, you have seen that in the weather forecast, that is the agriculture advisory services, they have made it sending the information to the farmers, and they are getting benefited with the weather information. But in case of other informations, still uh, no work has been done, or with the farmers it is still we are in experimental mode. But the future is very bright, that in coming years it will be this technology will be very much useful, and informations will be, we will be able to provide to the farmers. So many agriculture startup or startup in digital agriculture will be coming in the coming years, and providing those informations to the farmers. And that is not very that is not far away, and very soon we will do that one, and that is the demand of the time, because the 21st century we have to live with the digital agriculture. So thank you all for listening us listening me to for these lectures, and I hope you have enjoyed these lectures. And I welcome you all for the Indian Institute of Remote Sensing. If you get the time, so you can come visit the our institute and interact. Many more technologies there available, and which we can you can get benefited out of that one. Okay.
Good afternoon once again to all the participants. So, now we have come to the last lecture of this particular workshop. So, for the coming next 1 hour, we will be nearly 1 hour, we will be discussing about soil quality assessment, the mapping and modeling concept. What are the different approaches involved in the mapping as well as modeling of soil quality, uh, adopted at different scales, including point scale, field, regional, as well as other scales, and what are different approaches, techniques, use of remote sensing data, and all those things. So, as you might be already aware, soil quality index is basically how good the soil will perform its different functions. So, the soil functions are nothing but the various services provided by the soil resources. So, the healthy soils are known since ages to provide clean air as well as water, bountiful crops and forest, productive rangeland, diverse wildlife, as well as beautiful landscapes. So, the different soil functions commonly and widely adopted and accepted are nutrient cycling, which is the ability to store, moderate, as well as release and cycle the different nutrients as well as elements, organic as well as inorganic. The next is the water relations, the role played in water relation. That means in the role of soil in regulating the drainage, flow, and storage of water as well as the solutes. Partitioning the water for groundwater recharge as well as use by plants and soil animals. Next is the biodiversity as well as habitat. That means the soil supports the growth of a variety of plants, animals, microorganisms, etc. by providing a diverse physical, chemical, as well as biological habitats. Then the filtering and buffering, because the soil can act as a filter to protect the quality of water, air, as well as other resources. The toxic compounds or the excess nutrients can also be degraded and thus making it less available or unavailable to various microorganisms as well as human beings, as well as their entry into the various other ecosystems like the water, air, and other systems. In addition to all these things, it provides us the medium for providing the physical stability as well as support by allowing the passage of air and water, withstanding erosive forces, as well as providing a medium for plant growth. Apart from this, there are certain alternative soil functions also, which is out of the scope of this particular lecture. So in the morning lecture also, we have discussed about the different factors affecting. So I will not be discussing much about this. So only thing I want to refer is that we have inherent soil quality controlled by mainly the soil forming factors, as well as the dynamic soil quality, which is mainly influenced by the various changes in the management practices, as well as different aspects related to drainage, cropping practices, and others. This diagram indicates the various abiotic as well as the biotic factors constituting to soil quality in the soils located at the different portions or the different parts of the world. So if you see or if we consider the entire world as a combination of mean annual temperature as well as the mean annual precipitation regions, we can say the deserts, the desert ecosystems which is at the bottom, or the soils in the deserts, they mainly have a very less amount of annual precipitation, which is very near to 0 or 0 to maximum up to 10 or 50 millimeters per year. Whereas the temperature can have a very wide variation starting from minus 15 degrees Celsius to even up to 15 to 16 degrees Celsius, which is the mean annual temperature. Then we have the tundras, the climate, the temperature remains the similar in the similar range of minus 15 to minus 5, whereas the mean annual precipitation can reach even up to 1000 millimeters. So there, the animals or the population or the microorganisms as well as organisms, it widely varies from the predominant organisms present in grasslands, which are nothing but the earthworms as well as the ants, where the grasslands, they were found to have mean annual temperatures ranging from minus 5 to around 20 degrees Celsius with an average rainfall near reaching up to 1000. Whereas the boreal forests, we have the enterichids, mites as columbola, and they are characterized by a much higher annual precipitation range reaching up to 2000 meters, 2000 millimeters. Whereas the temperate forest, it can be deciduous as well as mixed, where the earthworms will be the major biotic factor influencing the variations in the soil property. Similarly, the tropical forest also. So this clearly indicates there is a segregation of the different types of soils or the different ecosystems, and these different colors indicate the different soil orders, starting from jelly soil, alphy soil, entisol, histosols, altisols. So from this we can say that the different orders or the different types or the different taxonomical groupings of the soils across the world, they are mainly determined by a combination of the biotic as well as abiotic factors, which is nothing but the nature of the predominant microorganism or the macroorganism, as well as the combination of annual temperature as well as the mean annual precipitation occurring in the particular region. And the soil quality, why we are interested in the studying, mapping as well as the modeling of soil quality, it is highly linked to the concept of sustainability. Understanding soil quality means assessing and mapping soil so that it functions optimally now and it is not degraded for future use. So by monitoring the changes in soil quality at regular intervals, a land manager or a person which is engaged in the management activities or a researcher, he will be able to determine if a set of practices or the management aspects whether they are sustainable or not. And when we talk about sustainable agriculture, it can be of different forms like economic sustainability. It is a combination of different types of sustainability like economic sustainability, social variability, as well as the environmental quality. And when we talk about the environmental quality, there are different components like water quality, air quality, as well as soil quality. And within the soil quality, it is nothing but a combination of the various physical factors, chemical factors, as well as the biological factors interacting in an optimal as well as a sustainable way, a sustainable rate as well as manner, along with the various influences of organic matter, pedoturbation, as well as the biodiversity. So the soil function ultimately affects environmental quality as well as agricultural sustainability. And when we talk about the sustainable development goals, there are different around 7 sustainable development goals which are directly related to the soil as well as indirectly to the soil quality aspect. And this thing we have discussed slightly in the morning, how we can assess the soil quality. So we know that soil quality cannot be measured directly. So we evaluate in the form of various indicators, which are nothing but the physical, chemical, as well as the biological soil properties, which can be easily measured, as well as which are highly sensitive to the variations in the management aspects. And now we have a question about, after doing all these things, why we want to assess soil quality. So the soil quality is evaluated to learn about the effects of management practices on soil function. And the reasons for evaluating soil quality, it can be categorized into different categories like first one is the awareness, generating awareness as well as giving education, the evaluation of practice effects as well as troubleshooting, assessment as a monitoring tool, the evaluation of alternative practices as well as the assessment as an adaptive management tool. When we talk about awareness and education, the soil quality assessment, it helps us in generating awareness about the multiple effects. It can be either direct as well as the indirect effects of various management practices. For example, if you take of tillage has got both direct as well as indirect effects, whether we can include as positive effect as well as negative effects. In one way, the tillage will help in loosening of the soil, reduction in the weed, improving the water quality, improving the water infiltration and other things. But on the other hand, it can also disrupt the aggregates. It can increase the decomposition of organic matter. So any activity, majority of the management activities have got multiple effects. So in one way, assessing the soil quality with respect to certain management aspects or practices, it will help in improving our awareness about the management. It will also understand the trade-offs of management options. That means it is the first step towards improved land management and public policy. That means when we are adopting a particular management option, what are the positives or what are the pros as well as the cons, we will be able to understand. And it will help in making some informed decision making. Coming to the evaluation of practice effects and troubleshooting, the monitoring of indicators, they may reveal the potential problems even before the painful symptoms occur. Sometimes these natural processes, they don't occur very fast or accurately, they will be very gradual. So sometimes certain indicators may reveal these are the problems which we are going to face after a prolonged use or a prolonged adoption of a particular management aspect. Then assessment as a monitoring tool, then the evaluation of the alternative practices. Suppose if we know that this particular management has got certain lacuna and we want to try with another management aspect. So the soil quality assessment, it will provide a framework for comparing the management trade-offs and deciding which management options provide the greatest good, whether for one's farming operation or at a watershed or a regional scale. So this particular graph indicates if we estimate the soil quality using the same set of indicators for one management aspect as well as the another management aspect, you will be able to easily identify which management will be giving a better alternative when compared to the others. Then similarly, the assessment also helps as an adaptive management tool. It allows one to examine the effects of making a change in management before actually committing full resources to that particular change. Suppose we want to adopt a new management practice. So before adopting that particular management practice or subjecting our entire resources for that particular management practices, we can do on a particular portion of a particular field or a particular area or a subset of the entire resources. We can examine the effects, then make the informed decision making whether we want to convert the management into entirely into the new one or we want to retain the older management regimes. This also we have discussed in the morning, the soil quality assessment approach. So at that time we were discussing about the selection of the different indicators. So once we select the indicators, what are the next things we will be going to do? We want to use these different indicator sets like the physical, chemical as well as the biological, including the non-soil as well as the site descriptions. And we will be establishing certain reference or the baseline values which can be used for further reference studies, as well as these the group or the set of soil quality indicators. They can be used for the calculation of the overall soil quality index. It can be further used for providing management advices, test and improving, as well as it can go into various levels of policy making also. And this we have already discussed that three different categories of soil indicators. We have physical, chemical as well as biological. I'm not going to discuss it again. So once we have the different types of soil indicators, we will be measuring from a particular area, whether it is a point scale or a field scale or a watershed scale or a regional scale. We will be measuring or computing the values related to large number of soil quality indicators. Once we get the soil quality indicators, what we are going to do next? Coming to the types of soil quality assessment tools, these are nothing but the practical tools to assess how the management practices will affect the soil. So the choice of the tool will mainly depends on the specific soil quality assessment as well as the land use objectives which we are interested in, the time, money and skills available to collect data. So the various categories of soil quality assessment tools widely adopted in the world mainly include the use of qualitative scorecards, then the use of field test kits, lab-based assessments, practice predictors, landscape level assessments, as well as multi-factor sustainability tools. So of this, the qualitative scorecards, field test kits, as well as the lab-based assessments are the most widely used and the most widely adopted throughout globally, whereas the others are limited and developed only in certain regions only, mainly in the Western countries. So the qualitative scorecards, they provide the list of observable soil indicators. They are mainly often developed by the farmers, not from a very strictly scientific point of view, by from the field observations as well as that local wisdom or the traditional knowledge of the farmers, and that are qualitatively evaluated by various land managers who work in close relationship with the farmers repeatedly over time to monitor the changes in the quality. Then coming to the use of field test kits, any sort of in-field soil test conducted by land managers to provide semi-quantitative data like the ones we discussed. Majority of the physical, chemical as well as the biological tests which are widely used or widely conducted preliminarily in the field, they mainly consist of the part of field test kits. Then comes the most widely used and the slightly from an accuracy point of view much more quantitative thing, which is nothing but the lab-based assessments. The assessments are mainly based on the estimation of various indicators requiring more specialized equipment or more precise measurement than possible with field test kits, such as the computation of microbial biomass, carbon, soil phosphorus, potentially mineralizable nitrogen. So these things, it's very difficult to estimate these different parameters in case of qualitative, if we are using qualitative scorecards as well as field test kits. An example or the most widely used lab-based assessment is nothing but which is referred as the SMAF, which is Soil Management Assessment Framework, this which we will be discussing in detail. Then coming to the practice predictors, they mainly use the research outcomes to predict the effects of management practices on soil quality. It is slightly towards a modeling part where we know the inputs, if so and so inputs are going or such management practices we are going to adopt, we will be predicting the research outcomes based on the empirical data observations. For example, the soil and water eligibility tool SWET and conservation measurement tool CMT. Then the landscape level assessments, they mainly use the satellite and remote sensing technology to assess the resource quality at large spatial scales. Using remote sensing to predict soil carbon storage is one possible use for this type of assessment. This also we will be discussing in the spatial regarding to the mapping of soil quality. It mainly comes under the landscape level assessment. Then another not much widely used, which is the multi-factor sustainability tools. It mainly combine the environmental and economic as well as the social indicators in addition to the various physical, chemical and biological properties. And these are mainly the logical outgrowth from the soil quality assessment of agroecosystems, because of the we are trying due to the important relationship between soil quality and sustainability. These mainly include the proposed sustainability index. So coming to the detailed discussion about the soil management assessment framework, it provides the site specific interpretations for soil quality indicator results. That means we will be collecting or measuring the accurate values for different soil quality indicators, how to combine these different indicators into a single unique value. All these things are coming under the soil management assessment framework. So every site specific interpretation, how the different indicators are important with respect to a particular process or a particular management practice or a particular soil function, it is provided by SMAF. As the definition of soil quality for a particular site mainly depends on your management goals, the climate, the crops as well as the soil type. A framework approach to soil quality indexing is very much required, and it is the ultimate basis of SMAF. And this allows for the necessary differences in site and goal specific interpretations of indicator results. So the same value for a particular result, particular soil quality indicator, it can be interpreted in different ways depending on the particular management goal which we are interested in, the in which climate we are addressing it, under which crop as well as under which soil type we are getting that particular value. So the interpretation changes from and based on these different conditions. So the index framework, from these diagrams we can see the index framework involves mainly three steps. The first one is the indicator selection. It is to efficiently and effectively monitor the critical soil functions. And the second one is nothing but interpreting these indicators in terms of soil function. That means using expected ranges determined by the soil's inherent capability. And the third one is combining these indicator scores into an integrated index. So that ultimately if we have around 10 indicators, ultimately combining all these things, we will be getting a single index value, so that the comparison between different things becomes easy, because we will be comparing a single value among the different management practices or different areas or different crops or different climatic regions. So the result is nothing but a relative measure of the soil's ability to perform the functions necessary for its intended use. So if you go through this diagram, the indicator selection. Indicator selection means we can choose a large number of indicators which we have discussed in the morning, but for a particular area, and if we are interested in a particular soil function or a soil management aspect, all the indicators may not be useful or may not be helpful or may not be required for assessment in a particular area. So first we need to identify critically by critically analyzing what soil function we are ultimately focusing on. Based on that, we need to identify different indicators among the large indicator dataset. So if you're having a large indicator dataset, which is nothing but the total dataset, using different methods, we can identify certain minimum datasets, or the minimum, that means a most important parameters, physical, chemical as well as the biological parameters, which can most accurately represent the soil quality function in a particular area. So the indicators chosen are mainly chosen based on the site specific factors. Then these chosen indicators in the minimum dataset, they will be interpreted or they will be converted into, they will be scored based on using different scoring functions for their interpretation. Then the scored different indicators, they will be combined for the computation of soil quality index. Coming to the process of indicator selection. So the as we already discussed, there are a large number of indicators available, but we will not be using all these at once. So the set of indicators which are used to determine a soil's quality at a particular point of time or in a particular case is known as, is called the minimum dataset or the MDS. So the two methods for MDS selection are expert opinion as well as using the statistical data reduction. So the expert opinion requires the expert knowledge of the system. So it will be by a person who is already working in a particular area or a long years of experience about the different intricacies related to the interaction between the various physical, chemical as well as the biological properties or the processes. So using a hierarchical framework, for choosing the indicators may help make the selection more systematic. And sometimes a multi-criteria decision analysis like analytical hierarchical process will also be used by different people. So mainly the management goals which we are interested in or which we are targeting to study, they mainly dictate the soil functions of interest, which in turn suggest related indicators. For instance, if the animal waste disposal is the goal in which we are located or which we are interested in for a particular field, then the filtering and buffering function of the soil becomes most important. And under the filtering and buffering, the indicators which are directly related to or which can give a better idea about the filtering and buffering function of the soil, for example, the organic matter content as well as pH, they will be chosen as the potential indicators. And similarly, the indicator set, they must be further refined according to the climate. In which area you want, which climate, the soil, plant community and other factors also will influence the selection of the indicator set. And the next method of MDS selection is the statistical data reduction. It can effectively choose indicators in diverse soil systems. It can eliminate the disciplinary bias, the personal bias when we are doing it by a person. That could be which can be a problem with expert selection. But it does assume that the appropriate indicators are in the original data set. So we obviously we require a minimum level of knowledge about what are the soil functions which we are interested in and what are the indicators which can probably give an idea about the efficiency of the soil in performing that particular soil function. So in the total data set, that much appropriate amount of indicators or the number of indicators should be there. Within that, doing certain statistical analysis, we will be selecting the minimum data set which can most accurately represent the soil functions. But the major weakness is that we require a large number of existing data set. And many a times the land managers or the people who are working for soil quality estimation, they may not be having access to the data sets that are suitable in size, either the number of indicators measured or the number of observations. And the statistical data reduction mainly rely on the use of principal component analysis, redundancy analysis as well as discriminant analysis. Coming to the second part of SMAF, which is the interpreting the various indicators. So for interpreting the various indicators, because the different indicators will be measured in different scales or the different units. Suppose in pH the value ranges from 0 to 14, whereas the electrical conductivity, it can be anything from starting from 0 to any value depending on the salinity, whereas the carbon value will be in percentage, whereas the nitrogen value will be in percentage. So all these are having all these will be in different scales in different units. So in order to bring all those together so that we can further combine them into a particular index, the scoring of these indicators are necessary. The scoring is necessary to interpret how each measure relates to the soil function of interest and to allow the indicators to be integrated by eliminating these unit differences. So in case of scoring, every observation of each of the indicators will be transformed for inclusion in the SQI. So suppose the different indicators, suppose pH, organic carbon as well as EC, these three indicators are present in the MDS. They will be scored into dimensionless values to normalize. It is basically a normalization procedure. We will be normalizing all the indicators so that the value within this particular MDS dataset of a particular indicator, they will range from 0 to 1. So all the observations of pH, electrical conductivity, everything will be, all the PEC values will vary from 0 to 1. All the pH values will vary from 0 to 1 as well as all the SOC. It is applicable to all the indicators present in the MDS. The values will be converted into 0 to 1. So for conversion of this scoring function, mainly they use non-linear as well as linear scoring functions are most widely used. And when we talk about soil quality index, the most widely used, there are three main scoring functions curves which are represented in these figures, which is more is better, less is better, as well as the midpoint optimum is better. So in case of more is better, it is nothing but the upper asymptotic sigmoid curve. That means the higher the value, higher its contribution towards soil quality. Less is better means lesser the value of a particular indicator, it is more towards good soil quality. And there are certain things like optimum is better. That means lower the value, very low values as well as very high values of that particular indicator is not good for soil quality, whereas the value optimum in between values are good for soil quality. Suppose pH, neutral pH is suitable for most of the functions in soil quality, whereas more is better, soil organic carbon, higher the organic carbon it is good, so more is better. Less is better, suppose electrical conductivity, lesser the electrical conductivity value, it is much better towards soil quality. So once we have identified the minimum data set, converted them into different scores using the linear scoring functions, Once the scores are given, the different indicators can be combined in a variety of ways, such as additive, weighted, or multiplicative indexes, ultimately resulting in the generation of various types of soil quality index, which is nothing but a ratio. Majority of them varies from 0 to 1 or the 0 to 100%. So the first one is simple soil quality index is nothing but the additive. The scores of for a particular point, the score of each of the indicators will be summed, it will be added, and like that it will be done for all the points. But the most widely used and commonly used is the weighted soil quality index, where the score of each of the indicator will be for a particular point or a particular pixel or a particular area, it will be multiplied by its corresponding weight. So for each indicator value, each observation, it will be multiplied by the score as well as its weight, and it will be done for all the different indicators in the minimum data set. They will be summed for getting the weighted soil quality index, and the value ranges from 0 to 1 or 0 to 100%, and the weights will be mainly assigned based on AHP or PCA, or different approaches are there. And coming to the various indicators used in the soil management assessment framework, they mainly include the soil physical, chemical, as well as the biological characteristics, which are mainly management sensitive and therefore dynamic. Currently, the SMA framework, it mainly includes 11 indicators with the scoring curves consisting of interpretation algorithms, some including logic functions also. So the 11 indicator sets which are widely used and included right now in SMAF is wet aggregate, macro aggregate stability, the bulk density, electrical conductivity, pH, sodium absorption ratio, high sodium soils, which are found in a high sodium soils as well as irrigated lands, extractable P as well as potassium, soil organic carbon, microbial biomass carbon, potentially mineralizable nitrogen, as well as the beta glucosidase activity. So it mainly includes 4 microbial or biochemical indicators: carbon, PMN, MBC, and all represented by Morris-Better curves. So coming to another slightly SMAF is the most widely used framework for soil quality index, soil quality assessment. Then another important soil quality assessment technique is the Cornell's, which is known as CASH, Comprehensive Assessment of Soil Health. It is also a farmer-oriented assessment tool similar to SMAF. It mainly evaluates the relative soil functioning with respect to crop production as well as their environmental impact. And most of the scores are effectively percentile ratings. All the scores will be converted into percentile ratings, comparing a measured value to a non-population distribution in a textural group. That basically it is defined on different textural group basis only. So earlier it was initially based on SMAF, but as the CASH procedure moved to a high throughput lab setting, it shifted to indicators with faster procedures like ACE proteins substituting for potentially mineralizable nitrogen, as well as the permanganate oxidizable carbon replacing for microbial biomass carbon, so that the analysis time can be considerably reduced. And there are certain other soil health assessments also, which are mainly restricted to NRCS or USDA under USDA area. So it mainly estimates the effect of, first one is the soil conditioning index, mainly estimates the effect of crop management on soil organic carbon levels only. It is designed to determine if the soil organic carbon levels would increase, decrease, or remain stable under a given management system. So when the they have did some comparison with SMAF also, when soil conditioning index was compared with the SMAF soil organic carbon indicator, so SMAF carbon was more successful in separating the tested cropping systems compared to the NRCA soil conditioning index. Similarly, another simple ratio based index is also there, which is nothing but the ratio of microbial biomass carbon upon the total organic carbon, which is used as an indicator to assess soil quality, and it is highly found to be more sensitive than the changes in soil organic carbon content also. Because this is because the microbial biomass carbon values, they change much more rapidly in response to management regimes when compared to organic matter, because the changes in organic matter take some amount of time, whereas MBC can change even within a few seasons or within a few months or a weeks also. Thus, the early stages of soil degradation, it can be easily identified by variations in the microbial biomass carbon rather than the changes in organic matter, which is more stable and subjected to fewer variations. So if our aim is to identify the soil degradation at a much earlier stage, so we can take some management measures, then MBC or simple ratio based index should be adopted. So with this, we have come to the theoretical part of the majority of the concepts which are most commonly widely adopted across the globe for the assessment of soil quality. Now we will just quickly see some of the case studies where people have used these different concepts which I have discussed for the spatial mapping as well as modeling of soil quality. This is one of our studies from Indian Institute of Remote Sensing only. So we tried to map the spatial variability of soil quality parameters in a watershed in a sub-Himalayan. The study was carried out in a 1,000-hectare watershed, in a hilly watershed in Himachal Pradesh. So these are the sampling points are also indicated. We conducted a grid sampling at every 250-meter grid. We collected a sample in the entire study area. Then similarly, we estimated the different soil quality indicators like organic carbon, all the nutrients except the physical and biological properties, nutrients, the texture, all these things we have done. And the IDW interpolation technique, it was used for generating the spatial distribution maps of organic carbon, stratification ratio, CN ratio, as well as soil quality index also. And coming to the computation of soil quality index, it was computed mainly based on the analytical hierarchical process as well as the spatial distribution was mapped to get a good overview about the soil quality data. And coming to the computation of soil quality index, these are the different parameters which were used based on the minimum data set. And we did the scoring based on the scoring function. Then the weights were assigned mainly using the analytical hierarchical process based on their function towards soil quality. And coming to the analytical hierarchical process or AHP, it is a very powerful multi-criteria decision-making process which enables to organize and analyze complex decisions and ensures the consistency in judgment. The pairwise comparison in AHP, it mainly enables the allocation of comparative rating between each criteria. That means each of the, if we have 5 indicators in the data set, each indicator pairs, they will be compared on a numerical scale. So based on the consistency, we will be assessing the weightage for each of these things, which is having a more weightage or which is having a more influence on the soil quality. Like that, the weights will be assigned. And the scoring was done based on the different scoring functions we discussed. More is better, less is better, as well as optimum is better. And these are the spatial distribution maps. If you see, we can especially map the individual soil quality indicator also. That means the soil organic carbon concentration is mapped. The stratification ratio, that means how the ratio between the amount of carbon in the surface divided by the subsurface. Then this is for individual points, we have computed the soil quality index, and the individual soil quality index from the different sampling points, they were spatially interpolated using the geostatistical techniques. And we could find that the soil quality index in this particular study area, they are more located in the higher elevation regions compared to the lower elevation. Similarly, it indicated a gradient in the soil quality index distribution with higher values. And large area of the watershed, they had the SQI values of 60% of the maximum possible value. That means out of 100, around more than 60. And which necessitates the adoption of better management practices so that we know which areas, if we want to improve the soil quality index of this entire area, which area we need to focus our management aspects or input management or our various management aspects. We need to focus on the lower areas which are having the lower values for soil quality index initially. And this is another study for the quantitative assessment of soil quality with respect to sustainable agriculture. They try to develop a spatial model for the assessment of soil quality based on 4 main quality indices. So combining the large number of physical, chemical, biological, as well as the geomorphological indicators, they have generated 4 main quality indices like the fertility index, physical index, chemical index, as well as the geomorphological index. They were combined in RS and GIS or the geospatial platform. So they have used the remote sensing derived NDVI parameter to assess soil quality in the study area. They extracted the landform units mainly by integrating a satellite image with a DEM. Around 48 soil profiles were generated for the uniform representation of the entire area. And they used the model builder function as well as an ordinary kriging interpolation. So by ultimately combining the physical, chemical, fertility, as well as the geomorphological properties of the study area, the SQI was generated. And ultimately the weighted additive index was generated. And these are the details of the 4 different indices they have used. Coming to the geomorphologic index, it is basically comprising of the various components related to the slope of the area, aspect, plan curvature, and profile curvature. Basically the landscape characterization. Then the fertility index mainly generated using the primary nutrients as well as organic matter NPK as well as the NDVA values. Then the physical index mainly derived mainly using the different physical soil quality indicators like the depth, texture, bulk density, hydraulic conductivity, water holding capacity as well as the surface stoniness. Then the chemical index was generated mainly using the EC, the pH, calcium carbonate, calcium sulfate, the exchangeable sodium percentage as well as using the CEC values which we discussed. Then the soil quality, digital soil quality model, it is basically the combination of the chemical index, physical index, the fertility index as well as the geomorphological index using this particular equation. And these were the ratings they have given for the computation of for the different variables which were or the different parameters which were included in the development of these different 4 categories of indices. And these are the some of the results how these rasters were processed, from which sources they were generated and they were interpolated. They were converted into rasters. They were reclassified mainly based on the scores as well, the scores given in the tables shown here. So, and finally, the different chemical, fertility, physical, as well as the geomorphological indices, they were also given the values. They were also considered into different, categorized into different classes, like whether it is very low, low, moderate, high, very high, into different classes. Ultimately, combining all these things, the final soil quality range of the study area was classified into the values which are the SQI areas where the soil quality index was found to have values less than 0.48, they were considered to be very low, whereas the values more than 0.55 were considered to be having a soil quality index value of very high. So this is the aerial distribution of the different area was the geomorphological index based on these classes, how they were classified. So very high, high, moderate as well as low based on this particular table. They have classified the entire area into the different classes of GI, PI, CI as well as the FI. Ultimately combining them, all of them into the soil quality index. This is the aerial distribution. So the soil quality was divided into 4 classes. That means the area having high quality, moderate quality, low quality and very low quality. And if you see this, majority of the area, nearly 50%, that is 49.23% of the total study area were found to have very low soil quality, and it was combined and it was compared along with and there was a very high agreement between the weighted additive index which we generated and the developed model, as most of the study area is classified as very low according to the developed model as well as the earlier data available. And most of the area is classified from an agriculture point of view. They were considered to be very poor for agriculture, which means that these soils have a lot of hazards such as very shallow depth, high amount of coarse fragments, low value of fertility indices. So ultimately the soils belonging to the class C5, they cannot be cultivated consistently due to the management process due to the inherent difficulties associated with agriculture. And this is another study where the multivariate approaches was used for the soil quality assessment. In this, mainly 2 methods for indicator selection was, as we have already discussed in the theoretical part. They have used the total data set as well as the minimum data set. Along with, they have used 3 soil quality indices: the additive soil quality index, weighted quality index, as well as the Nemoro quality index, which we have just mentioned before. And they have collected around 55 soil profiles from the area. 16 parameters representing different measurable soil attributes influencing the capacity of soil to perform various functions. They were also identified, and the principal component analysis was employed to establish the MDS, and the score ranging from 0 to 1 was assigned mainly based on the different scoring functions. Low is better, more is better, as well as optimum is better. And this is the overall. You can see the indicator selection. It is done using the total data set was converted into minimum data set. The indicators were considered in using scoring function. They were converted into scores. The scores as well as their weightages, they were converted for the generation of different quality indices like the additive quality index, weighted index, as well as the Nemoro index. And the soil quality were converted into grades and they were mapped. And these were the scoring functions they have used along with the different parameters. They have used depth, gravel, texture, different nutrients, gypsum, calcium carbonate, all these things. And these were the computation of additive quality index. That means score of each of the indicator, it was divided by the total number of indicators used in the index, and the such score ratios were added to generate the additive index, whereas the weighted index is nothing but the multiplication of weightage into score for each indicator and the summation. Nemoro index is based on the average as well as the minimum within the entire data set. Once we had this particular thing, the one-way ANOVA test was also done to examine the significant differences among the indicators and indicator measurements. Correlation analysis was also done. Ultimately, each soil quality index, they were classified into 5 grades like very high, high, moderate, low, as well as very low. The range of values for each SQI was divided by the number of desired intervals. And this is the table which shows the PCA analysis. So among the different indicators, the minimum data set consisted of these different indicator values which are underlined. They were only included in the minimum data set, and based on the eigenvalue, only the first 4 principal components were chosen, and which for the further analysis or the development of MDS, which explain nearly 82% of the total variance present in the original data. And the significant correlation parameters with significant correlation were removed, and the highest loading factor was selected. So ultimately, the total 16 physiochemical or the indicators, they were reduced into 4, mainly the sand, gravel, depth, as well as the exchangeable sodium percentage. And these were the soil quality grades generated based on that. And this is the additive soil quality index based on the TDS. This is mainly based on the additive soil quality index based on the total data set, minimum data set. Similarly, all the combinations. And this is another study, the development of, they have done soil quality index under arid and semi-arid region. They're using a medalless, this is mainly the Mediterranean region. It is widely used for land degradation assessment. Here they have used the digital elevation model as well as Sentinel-2 satellite image to produce landforms as well as the digital maps of the different soil properties. And this is the overall methodology: integration of Sentinel, DM data, generation of NDVI, the field work for laboratory analysis, different indicators. Ultimately, you have generated the soil quality as well as the land capability maps. And these are the class thresholds as well as index values given for the different classes, subcategories of the different indicators. So the models were interpolated for the spatial mapping of all the indicators. They were reclassified and they were assigned for the index, and ultimately the soil quality index was estimated using this particular equation, where the based on the soil texture index, gradient index, soil depth, drainage index, calcium carbonate, organic matter, as well as the soil salinity index. So these are the spatial distribution maps of the various physical, chemical, as well as the biological soil quality indicators. And this is the spatial distribution of the soil quality index as well as the capability index. And they found that mainly the land capability, majority of the area were found to have very less amount of soil quality were found to be comparatively poor. And the soil quality spatial model developed, they were accepted with the current situation, and they were highly correlated with the results obtained for the same area when compared to the land capability. So the spatial trend of the soil quality increases. There is a trend from the north to the south, from north to the east, and it is consistent. And the trend could be identified and managed because the majority of the area, the soil quality index was found to be influenced highly by the high percentage of calcium carbonate, exchangeable sodium percentage, salinity, as well as a low concentration of organic matter and intensive mismanagement of with respect to agriculture. Similarly, in one of the studies, a similar simple additive soil quality index was computed mainly for Chamarajanagar district of Karnataka. The main objective was to assess and identify an effective soil quality index indicator dataset among the various measurements. So they have done the different geomorphologic units were identified. The land use land cover mapping was done using remote sensing image. And based on the different physiographic units, the soil profiles were generated, and the thematic maps for various soil quality indicators were generated using geostatistical analysis. And the simple additive soil quality index was estimated. They were given threshold values based primarily on the literature review as well as expert opinion. So ultimately, the soil quality index was generated using this particular equation: the soil quality index of the particular point, the minimum within the entire area, as well as the maximum. And these are the different soil unit description as well along with the associated taxonomy. These are the physiographic units, and this is the spatial distribution map of the soil quality classes within the Chamarajanagar district. So the weighted overlay was used. So they found that the high soil quality area occupied 26%, whereas the moderate soil quality area occupied 41% of the area, and so majority of the area were found to have moderate to high soil quality within the entire district. Coming to one of the another case study where the spatio-temporal, that means how the soil quality changes with the location as well as during the different time periods. The spatio-temporal dynamics of soil quality was estimated in the desert area using machine learning as well as using the digital soil mapping, which is an currently upcoming technique based on the geospatial as well as the machine learning models. It was widely adopted. So they tried to investigate the spatial as well as the temporal changes of soil quality in the study area between 1986 to 2030 in the central Iranian desert region. So they mainly investigated the spatial and temporal changes of soil quality. They have generated a large number of environmental covariates representing various factors of soil formation were generated from various sources including remote sensing and others, and around 200 nearly 200 topsoil samples were collected using a particular sampling strategy called CLHS hypercube sampling, and the key indicators of soil quality they were identified and measured. If you see the particular steps, it mainly included the covariates representing the environmental condition of the present area, present time period when the sampling was done. 2016 was generated. Based on the covariates, the sampling strategy, if you the sampling locations where we should do sampling were identified using Latin hypercube sampling. At the locations, either the field-based physical soil quality indicators or the chemical samples were collected, and they were subjected to principal component analysis. The sensitivity analysis was also done, and the relationship between the different environmental covariates as well as the soil quality indicators were established, and using a random forest model, which is nothing but a machine learning model widely used in digital soil mapping technique. And finally, the model was used for the preparation of the spatial distribution of soil quality index along with the uncertainty estimation. Then the covariates representing the different time periods like 86, 99 as well as 2010 were replaced into the model, and they were used for the prediction of the soil quality maps for those corresponding periods, that is 1986, 99 as well as 2010. Similarly, certain modeling was done for the generation of covariate and environmental conditions for 2030, which is in future, thus predicting the future scenario of soil quality index. So here the soil quality index generation included the principal component analysis, and this is the list of around nearly 69, if I'm correct, yeah, 69 soil quality indicators. It mainly included the things mainly generated from terrain indices, then the remote sensing based, then certain Euclidean distances, geological information, groundwater quality parameters, everything. So among these different type, a large number of indicators, which are all the things which are widely influencing soil quality, they were identified using the screening method. The RF model was trained to make spatial prediction for 16. Then the fitted model, the same fitted model, by replacing the input data, they were used for evaluating historical and future patterns. And the environmental data representing 3 time steps, they were also used. And the predictions for generating the future scenario, the groundwater parameters for the future, they were projected using equation relationships, and the future land use were applied as new inputs for making the forecast of soil quality for 2030. And this is the selection of minimum data set. So these were all the parameters they have used. Based on the principal component analysis, they have chosen only these are the parameter, these values correspond to the parameters which are chosen in the minimum data set. They were identified using PCA, using scoring functions they have used. Then good correlation was found to be observed between the measured as well as the predicted soil quality. We can see for each point what is the predicted value and what is the computed or the observed value. It is plotted. Except few points, majority of the prediction as well as the measured values, they are very close to each other. And these are the scoring functions which were used for the indicators which were identified in the minimum data set. Less is better, more is better, and all. These were the upper and lower limits they have used. Then for the prediction of the future scenario, they have predicted the future groundwater parameters. They were forecasted using the historic groundwater quality information by generating a linear relationship. Similarly, they have also simulated the land cover changes, how the land cover will be occurring in 2020 using a CA Markov model using the past land use land cover observations as well as the data. And these are the spatial distribution maps of the soil quality index in 1986, 1999, 2010 as well as the 2016. So we can see that the good soil quality index, which is indicated by the value dark blue color as well as the green, the red indicates the lowest soil quality index area. So we can see that in the year of 1986, the good soil quality, it is primarily located in the southern as well as the western part of the area. That means the soils in this area, they were found to have very lower soil quality, soil salinity as well as higher or soil organic carbon. Similarly, as we move from 86 to 1990, we can see that majority of the area which were earlier under very good soil quality, they have right now come into moderate, or the soil quality has decreased or degraded. There is an increase in, it is corresponding to an increase in the land degradation as well as the decreasing soil quality index with time during 1999, 2010 as well as 2016. That means the areas characterized as very low class, they have been increasing continuously from 86 till 2010. And these were the different soil groundwater quality parameters like the bicarbonate, sodium, bicarbonate, electrical conductivity, sodium as well as a sodium absorption ratio. This is the spatial distribution maps or the future predictions mainly based on the linear relationship. And these future predictions were used for the computation of soil quality index in the future scenario, along with the future scenario of land use land cover. And this is the future predicted soil quality index spatial distribution for the entire study area for the year 2030. So we can see that when compared to 1986, 90, 99, 2010 as well as 2016, there are more and more area is coming under very low soil quality index. That means that during the entire period of 1986 to 2030, the aerial extent of the very low soil quality index, that means indicated in the red color, less than 0.4 value, it has increased nearly 16 percentage. There is a 16% increase in the very low soil quality area as we move from 1986 to 2030. While the extent of the good soil quality index, it has lower decreased by around 75%. That means the soil quality is degrading at a very alarming rate. That means it is or we can say that it is progressively, the soil quality in the particular area is becoming increasingly or progressively becoming much poorer. Here also we can see in 1986, you can see the green indicates the very good soil quality indicator class. You can see the depth of this green portion is constantly decreasing as we move from 86 to 2030. So such the results of this study with respect to the soil quality changes, it can be used for various applications like the land evaluation of the area, various environmental studies for identifying the various root causes in the area, whether it is because of salinity or the human induced management practices or any other things, as well as for the integrated planning as well as management with respect in order to properly as well as reasonably utilize the natural resources as well as reduce the future soil degradation in the particular area, which is very important from a sustainable use of natural resources as well as for the sustainable agriculture production point of view in these arid desertic ecosystems. So with this, we have come to the end of this particular discussion related to especially soil quality assessment, related to the mapping as well as basically mapping as well as modeling of soil quality. So it mainly include the mapping as well as modeling aspects of soil quality. It mainly involves the spatial distribution mapping. It mainly involves the spatial observations, combining them or generation of spatial databases, spatial distribution databases of soil quality indicators individually, either using geostatistical methods or using various machine learning or artificial intelligence based digital soil mapping techniques, or it may also include various modeling approaches like the land use land cover modeling for the prediction for the future scenarios and a number of aspects depending on the purpose or the soil functions in which we are interested in or we are targeting them. So that's it from my side. So I hope you had an overall idea about what are the different concepts or what are the different types of work people are undertaking from the research community related to the mapping as well as modeling of soil quality on spatial domain. Thank you all. So, so welcome all to this particular the small interaction session where I will be trying to answer some of your queries, most of the queries. So regarding the first lecture, inaugural lecture, based on the concepts and approaches by Dr. Suresh, someone has asked, Manas, can we find the soil pollution by satellite data? Uh, Identifying soil pollution by directly from the space-based satellite data becomes very difficult because majority of the times the soils will be covered with some cover. Until unless if it is a mining area or something, we can easily find out. It's difficult. But in a mining area or a big mine area and all, and so mainly what we use is the indirect thing using some proximal sensors or other things. Then we will correlate with remote sensing data and go for spatial mapping. Otherwise, we can indirectly identify the vegetation degradation happening due to pollution. How can we increase the carbon content of the soil? The most important aspect for increasing soil carbon content is nothing but the addition of organic matter as well as reduction in the organic matter mineralization by reduced tillage, addition of more organic matter, maintaining optimum moisture content and other activities. How can we solve the waterlogging problem as soon as possible without delayed much time? So the problem of waterlogging is basically, it's a very complex phenomenon because it's mainly characterized by the land characteristics. If the majority of the area where the waterlogging occurs, they are mainly local depressions. So obviously the water from the surrounding area will accumulate in the particular area. And if possible, we can go for certain subsurface drainage also, but it comes with its own cost as well as issues. Why soil testing is expensive? So I don't think testing is very much expensive. It depends on the parameter you want to estimate. So there are different various soil labs maintained by the government, public sector soil labs, where we can the soil testing is it can be done with very nominal cost. Maybe within 500 rupees or something, you can do many. The soil testing, I don't think it is very expensive if we are going for any government funded labs. Are there any benefit of rainwater harvesting? I don't think these majority of the queries are not at all related to the today's lecture anyway. Obviously, rainwater harvesting can maintain the water, can maintain the can increase the water availability for the entire area for a prolonged time. More use of pesticides and fertilizers in soil can also create a problem. Obviously, it can create a problem because they may be leaching. How can we solve? The only solution is use only the optimum amount of fertilizers and pesticides at the required time period. Otherwise, there are chances of the residue as well as going into the waterways. Can organic way of cultivation practices help to revert back the lost soil health? I will not say only the organic way of cultivation practices can do it. We need to, in my because organic way has its own issues because the cost of cultivation will go very high. So the adoption on a large basis for all the farmers, it becomes a very difficult thing. Obviously, they can improve the soil health and other things, but the cost involved will be slightly high. How to enhance fertility? So fertility is basically integrated nutrient management, addition of organic matter along with the cultivational practices as well as fertilizers. Is it feasible to infer similarities in soil composition based on factors like vegetation density, slope? Exactly, I don't know what he wants to ask. Truth studies and laboratory studies. Obviously, that is basically related to the generation of physiographic groups. What is the role of conservation agriculture? The same thing. Increasing the organic matter input, reducing the cost, application of fertilizers and other things at the optimum level at the optimum time. How can overcome from deficiency of nitrogen without the use of fertilizers? It becomes difficult. You need to add either organic or inorganic, something you need to add. Is there an alternative way to increase nitrogen? The only way is either use fertilizers or any other addition of residues. Otherwise, biological nitrogen fixation you need to improve. What are the bad effects of less nitrogen on soil health? Obviously, the productivity will be going down. How to measure soil quality? I think the entire lecture, second lecture was based on that only. Can we improve the cation exchange capacity of the sandy soils? Obviously, we can improve. We can improve by the addition of soil organic matter because the clay content is already low there. Coming to the next lecture on the measurement of soil quality, soil health and quality. What are the types of soil? I think it's a very basic question. The different types of soil, it can be taxonomically different or it being based on the textural classes also. The soils can be different, mainly coarse textured, loam textured, medium textured as well as fine textured. What MBC stands for? MBC stands for microbial biomass carbon, that we have discussed already. And coming to the questions in the third lecture, what does proximal sensor find? Proximal sensor is nothing but it's not a name of an individual sensor. It is a group of sensors where we will be taking the measurements in very close proximity to the soil, or either by touching the soil without any chemical analysis, using the rays or the radiation measured or the signals from the scent and the reflectance. We will be using the measuring different components. For example, one of the thing is portable XRF, then the color sensors. So proximal sensors are not as individual sensor. It is basically a name for the sensors which we are used at a ground level, very close proximity to soil. Best crops for agriculture production. It depends on your area, the price. So it's a very different thing. Whether proximal sensors are available for research purposes, obviously it's are available. You need to purchase it. What about if robots starts to do agriculture? So I don't have much idea what will happen if robots do. They will be good in doing repetitive works more efficiently. What is weather forecasting? That is basically predicting when the weather is going to change, when the water, how much amount of rainfall is going to come well in advance, so that we can manage the thing. Could you explain in detail about co-kriging? It is basically using a for kriging you are using another easily measurable correlated variable. Can you explain soil grid sampling for an agricultural farm? Suppose the farm will be entirely divided into square blocks or grids, and you will be collecting sample from each of the grids, so that the entire area, the variability will be covered. Is it really helpful or feasible to get soil quality indicators based on only color? So basically this color concept, all those things are very new. We are trying, many people are trying. It's not that it will be completely a replacement, but it can give a good amount of comparative assessment between two different fields if within the similar area, because the color or the baseline should be the same. Can we proceed similarly in assessing water quality also? Exactly, I have not ever worked in water quality. Obviously, water quality has its own parameters. Basically, all this quality assessment is mainly based on different indicators, whether it is pH, salinity, or a number of things. And coming to the last session, there is one query: is much productivity possible without pesticides and insecticides? It's basically the pesticides and insecticides are a part of agriculture production. Whether it is a synthetic chemical or an organic material, that is the difference. So in one way or the other way, we should have measures to control the pest. So whether you use any chemical or non-chemical methods, that is inevitable. All organic pesticides are healthy for soil. Organic pesticides, everything has their own residues. So how long these residues will remain, or what about the leaching? Because ultimately, organic or inorganic, All those things are basically chemical composition components only. Software name for soil mapping. So basically, so there is no as such software for soil mapping. We do based on the analysis for the remote sensing and GIS analysis. We mainly use IIRS Imagine as well as ArcGIS, which are commercial softwares, or QGIS, which is an open source software. Similarly, for digital soil mapping, we mainly make use of ArcGIS, R software, which is an open source. How to compare organic carbon based on color? Vertisol will be black in color by nature. Inceptisol will be light in color. So how to estimate? It's a very good question. That's the thing which I mentioned earlier, because the comparison can be provided. It cannot be done in all the different types of soils. In lighter background soils, then the variations, because the baseline will be same. That means Inceptisol, the baseline or the background color will be same or lighter in color. Then there, in such cases, the increase in soil organic carbon can lead to darkness. That is the assumption, and that is the thing which is proven in various laboratory as well as the small scale field based studies. In vertisol, I think it will be very difficult, because already the background is already dark in color. So the variations, the color variations because of the variations or the changes in soil organic carbon also will be very, very less for the color measurements to identify. So with this, we have come to the, I think I have answered all the queries. If any more queries are there, you can just send a mail to us. We will be replying it. So I hope you had a very fruitful session. You had some overall understanding about the soil health, the measurement, as well as the varying approaches used for soil health measurement as well as modeling, including the use of remote sensing, the measurement of individual indicators, and many a number of things. So with this, I think we can conclude, because all the queries I think I have answered. So I don't think any queries are left unanswered. So thank you all for joining as well as registering for this particular course and making this this workshop a very good, very grand success. Thank you, and we hope you will be showing the same amount of participation and as well as interest in for all our future programs also. Thank you all.